primary technique for hiding malicious execution inside legitimate processes. Instead of running a standalone malware binary, the attacker writes shellcode or a full PE image into the memory of a trusted process like Explorer.exe or svghost.exe. The injected code runs under the victim process identity, bypassing process-level detection and inheriting its network access, privileges, and trust relationships. Windows memory is organized into regions tracked by the virtual address descriptor tree, a red-black tree stored in the process structure. Each VAD node describes one contiguous memory region with its base address, size, permissions, and whether it maps a file or is private anonymous memory. Injected shellcode almost always lands in private anonymous VAD regions with execute permissions, an immediately suspicious combination. The malfind plugin is Volatility's primary injection detector. It walks the VAD tree of every process, identifies regions that are private, executable, and not backed by a mapped file, then dumps the first bytes and checks for MZ and PE headers. Any region that is executable, not file-backed, and contains a PE header or high-entropy shellcode bytes is a strong injection indicator worth triaging immediately. Process hollowing is a stealth technique where the attacker creates a legitimate process in suspended state, unmaps its original executable from memory using ZW unmap view of section, writes a malicious PE image into the now empty address space, and resumes execution. The process name, PID, and parent relationship all appear legitimate, but the code running inside is entirely malicious. Malfind catches the PE header in unexpected memory. DLL injection via LoadLibrary is the most common injection technique. The attacker calls virtual-alloc-x to allocate memory in the target process, writes the DLL path with write process memory, then creates a remote thread pointing at LoadLibrary A. The malicious DLL loads into the target process and runs its DLL main. In memory, the injected DLL appears in the DLL list but with a suspicious path, often temp directories or no path at all. Reflective DLL injection bypasses the Windows loader entirely. The DLL contains its own loader stub that resolves imports, fixes relocations, and maps itself into memory without ever touching the file system or being registered with the OS module list. The injected DLL is invisible to standard DLL enumeration. Malfind detects it because the memory region has execute permission, a PE header, and no backing file object in the VAD. Process Doppelgänging abuses the Windows transaction mechanism. The attacker opens a transaction, writes a malicious file into it, maps the file into memory as a section, then rolls back the transaction. The file never exists on disk, but its image is now mapped in memory. This evades file-based AV scanners completely. Memory forensics catches it because the VAD entry has an unusual transaction-backed file object. Thread injection via create remote thread is straightforward but noisy. The attacker allocates shellcode in the target, then calls create remote thread with the shellcode address as the start routine. Thread structures record the start address of every thread. A thread whose start address falls inside a non-file-backed executable VAD region with no corresponding module name is a definitive injection indicator detectable with Volatility Threads plugin. Atom bombing is a data-only injection technique that uses global atom tables to transfer shellcode. The attacker stores shellcode in the Windows global atom table using global atom, then triggers the target process to copy it into its own memory via an asynchronous procedure call. APC-based injection leaves the shellcode in memory regions that appear allocated by the target itself, but still show up as anonymous executable allocations. Shellcode signatures are byte patterns characteristic of bootstrapping code, hash-based API resolution loops, egg hunters, getPC techniques using call pop, and decoder stubs for encoded payloads. Volatility integrates with YARA, allowing you to scan all process memory simultaneously for shellcode signatures. A single YARA scan against known shellcode families across an entire memory image in one pass catches both file-backed and injected code. PE header analysis confirms whether an injected region contains a full portable executable. A valid MZ header followed by a PE signature at the offset stored in the DOS header confirms a mapped image. The PE optional header reveals entry point, image base, and section table. When malfind finds a PE header in an anonymous executable region, you can dump it with proc dump or wadump and analyze the import table offline. Memory permission analysis is a fast triage method. Page_execute_readWrite, the RWX permission, is extremely suspicious because legitimate code almost never needs to be simultaneously writable and executable. Shellcode stagers typically allocate RWX memory, write the payload, then execute it. The VAD protection field stores Windows memory protection constants. Filtering the VAD tree for execute_readWrite across all processes quickly surfaces the highest priority injection targets. The injection detection chain: first run malfind to identify suspicious VAD regions. Then correlate with the process DLL list using dlist to find DLLs with no backing path. Cross-reference with STRI to check parent-child relationships. Dump suspicious regions with wadump. Scan the dump with YARA and submit to a sandbox. Finally check command line and handles for evidence of the injector process that spawned the injection. The detection matrix for code injection, process hollowing appears as a PE header in the main executable VAD. DLL injection shows an extra DLL with a suspicious path or no path. Reflective injection appears as an anonymous executable PE. Thread injection appears as a thread start address in non-module memory. Shellcode appears as high entropy bytes in executable anonymous regions. All are detectable in memory without disk access. Your Vol.7 command toolkit: malfind finds injected code and shellcode. Dlist lists loaded DLLs per process including path. Threads shows thread start addresses. vadinfo dumps the full VAD tree with permissions. wadump extracts a specific VAD region to disk. YARA scan runs YARA rules across all process memory. Vol.8 covers network-based C2 frameworks and their memory artifacts.